statistics lesson. Our learning objective this time around is to construct and interpret diagrams for continuous discrete data and continuous data, i.e. histograms with equal and unequal class intervals and cumulative frequency graphs, and know their appropriate use. So again, we've talked about we talked about last time ungrouped discrete data. So I hope you remember what discrete data is. It's stuff like, it's when we have a, I guess, unit of measurement that can't be broken down any further. So an example of this might be, say, the number of lessons I have for school in a day. So so say kind of on Monday I've got, say, 3 lessons, right? On Tuesday I might have, say, 7 lessons. So I've got loads of frees on Mondays. On Wednesdays it might be 5. On Thursday it might be, I don't know, it's basically 1, so I've got the day free. And on Friday it's, say, 6. So again, I can't really have half a class, so this is discrete data. But I could group this together, so I could say kind of I could group this into the days I have 1 to 3 lessons, so that'd be Monday and Thursday. So 1 to 3 is that, so which is Monday and Thursday. Whereas I could then group it into, say, the days I have 6 or more, or even 5 or more. So these 2 and this one. So Tuesday, Wednesday, and Friday. So again, I've grouped the discrete data. I could also not group it together. I could just say ungrouped data would just kind of look like this, I guess. But despite it being discrete, which is what we talked about last time around. And then we can have grouped continuous data. So this might be something like the ages of people. So for example, let's say actually better yet, let's talk about say money, right? So money's can be continuous, I guess. You might say kind of it can no longer be less. It can't be less than a penny, but you could argue you can have less than a penny. So sometimes the definition is a bit confusing. But I'd say money is continuous because you can have £131 and 5 pence or something, right? So that's continuous, I guess. And you could in a sense you can have you can't physically own half a penny, but you could be sharing the penny among 2 people, for example. So if you said kind of the money people had, you could have that say people earning a certain salary, for example, in a year. So you might have a guy who's earning loads of money. Say he's earning £100,000 in a year, whereas someone who might not be earning as much. So let's say we've got A, B, C, and D. Let's say A, B, C, D, and E. A is earning 100,000. B is earning I don't know. Well, B's not working right now. He's a student. So he's probably losing money in terms of getting student debt, but he's earning no money. C is, I don't know, maybe earning £20,000. He's only working part time. D, let's say, I don't know, let's just say 45,000, and E, let's say 80,000. So again, this is of course the continuous data, right? You can earn 81,000, 80,000 and a half, or whatever, right? But you can of course group this together. So you can say, if you say kind of the people earning 0 to, if we say money is how much they're earning, so it's people earning at least equal to 0 or less than, say, 40. So that would be B and C. Earning more than or equal to 40, but less than, say, I don't know, 60,000. So that would just be D. And then those are earning that more or equal to, say more than people who are just earning more than £60,000. There's no upper range on that. So if we add F, or gajillionaire or whatever, he's earning, let's say, I don't know, 100 million a year, right? He'd also be in that group, in that final group of A, E, and F. So yeah, that's what kind of we mean in terms of group discrete and group continuous. It just means that we know what continuous versus discrete stuff is, and grouping just means that when we add a range like this. So one of the things we have is the cumulative frequency table. And cumulative frequency, well, that means kind of the frequency of a certain of this group and kind of anything before it in that sense. So look, you've got in this group you have 140 to 150, but now you've got 140 to 160. So as you can see, kind of the group keeps extending and extending. So it's cumulative in the sense that you keep adding the stuff before it. So this might be worthwhile in, say, again in the wages that people have, or perhaps in the height people have, because kind of it's an ascending thing, and then we can think, oh, if we measure this population, and by the time we get to say 200 centimeters, okay, if this, I thought this may be people, but let's say it's a tomato plant, and tomato plants, let's say they really get above 200 centimeters, we'll know kind of by the end of it that the total number is whatever, and kind of that doesn't really increase. And as you can see how when you plot this, you can actually kind of just by looking at it, you can infer quite a bit of data. So what you do is you say, okay, between 100 and 150, the cumulative frequency is 7, as it says here. So that means in the whole range between 150 and 170, there's going to be a total of 7. So we know at 150 that there's anything below 150 is 7, because that's 140 to 150, right? So then we'll go to 150 and plot 7. So 5, 6, 7. Now we can go to 160, and it says everything less than or equal to 160 there's 17 of them. So we go to 160 and then plot 17, and kind of just repeat that process. 1, 2. Sorry. I've always struggled with this kind of graph paper. 1, 2, 17. Just in terms of it always somehow hurt my eye. I don't know why. And in general, what you do is you look at this second number and you plot the cumulative frequency. Sometimes they try to catch you out and they'll say frequency, and in that case you have to add them up to get cumulative frequency. So to get the cumulative frequency of this one, that'd just be 7. But if they said frequency and you'd have to add another column of cumulative frequency, this would be 7, this would be 17 plus 7, this would be 32 plus 17 plus 7, and so forth. So watch out for that kind of stuff. So next we have 32 for 170. We got 170 and then 31, 32. 51 for 180. 180 and then we plot 51. 57 is for 190. And 60 is 200. And when you connect these, you should do it with a smooth curve, or I believe you can actually use a kind of a ruler and do point to point, but you can do actually either of them in this case, but I tend to do it with a smooth curve. And if you think about kind of in the middle, what you're doing is you're kind of thinking, I guess it's what we call interpolating. You don't actually know kind of the number of kind of people who, the number of tomatoes which are less than or equal to 155, right? You don't know the cumulative thing there. So by kind of drawing a line between them, you're saying, it's going to be between kind of this number and this number, right? Because by the nature of cumulative frequency, but you don't know where along it is going to be. So by drawing a straight line, you're saying, oh, it's exactly going to be kind of there, which isn't necessarily true, but we do kind of have to interpolate it for, kind of have to do, I guess, just to join the lines. So we're kind of, implicitly we're saying that when we draw the line, we're saying, it's around there somewhere, and we're just assuming it's kind of in that if we kind of connect that straight line, I guess, or if we're dealing with a smooth curve, kind of, so that it's a smooth curve. And also kind of, this will of course be 0 here, because, I think we've been told, you can kind of assume that none of them are going to be less than 140, I think. If there was going to be kind of less than 140, then it would say kind of, less than 140 is that. So, and it even says, that, and this is 7, that, all these 7 are greater than 140. So there's going to be clearly none mentioned in this table that are less than 140. So you can see here everything is greater than 140, right? So you plot that 0 thing as well. So you can just connect this with a smooth curve or a line to, getting a ruler out and connecting the points. I've always preferred to do it with a smooth curve, but it's a bit harder to do on this kind of writing pad. I think most of the time you do see it does end up being a smooth curve like this. And there we go, we've got cumulative frequency stuff. And sometimes you'll be asked to pick some, read data off of this. When we talk about interquartile range and stuff like that, well, that you'll have to you apply that in this situation, but that's kind of for a future video. Next, we've got something called histograms, and so this table shows. Well, actually, if we go back here, again, this is what we were talking about: continuous and ungrouped, continuous group data, because height is continuous. If we look here again, age is also continuous group data. So again, we have a histogram. So the table shows the information age for 80 teachers, and it's saying, for there's 20 teachers which are aged between 20 and 30, and 22 between 30 and 35, and so forth. That's what this thing is saying here. And with a histogram, what it looks like, if we actually, I go to a histogram first, I'll show you what it looks like. And it looks like this. And on the left, you'll have frequency density, and on the right, on the bottom, you have kind of whatever this is, so, the height, for example. And this compares this is different to a bar chart, because for a bar chart you usually have a category. You'll say say sports or something like that, or kind of something like 0 goals, 1 goal, something like that, which is I guess a pretty obvious category. This, you've got group data, and also because sometimes in these frequency tables, because you have differing sizes of these groups, if you were to plot, say 20 to 35 as kind of a box, as in say in a bar chart, right? You'd say, oh, this is, you plot 20 to 35 here, and that we can plot 20 here, and then again same. So say this is the category 20 to 30. This is the category 30 to 35, which are clearly different things, right? But you could you can say 20 here, whatever, say that's 20 for example, and then 22 here, right? Which fair enough, actually does kind of make sense, right? But it doesn't take into account the differing width. So what we do is we think about kind of, oh, so there's a range of 10 here, but there's only half the range here. There's only 5 here. So having a frequency of 22, it kind of means it's a lot more common in the 30 to 35 thing, and then kind of between 20 to 30. So here there only looks like a difference of 2, right? So you think, oh, having an age of 20 to 30 is pretty common to having, and pretty similar to having an age of 30 to 35, or from a probability point of view. But you have to account for the fact that kind of this is a way smaller range, right? So it's, I guess, even more likely. Or maybe if we consider, say, 50 to 65, this is larger than that, right? And it's 9 versus 20. But you might want to think about 9, but there's 15 years here, but there's only 10 here. So you can't just compare 9 and 20. You ought to compare some sort of ratio between these two numbers. And this is where frequency density comes in. Frequency density is equal to the frequency divided by the width of your group. So the width of this group is clearly 10, this is 5, this is 5, this is 10, and this is 15, right? And you kind of just have to plot that. So, you do frequency density, FD, you do 20 divided by 10, 22 divided by 5, what is that? 4.4, 16 divided by 5, 3.2, 13 divided by 10, 1.3, 9 divided by 15, 0.6. And you've got frequency densities now. Now you have to kind of Command Z that. And now you ought to plot this. So on the left, you'll write frequency density. And on the bottom, you'll have age. And then you want to have that so that there's a constant scale here. Instead of how I mentioned in the bar chart, you could have any kind of each square being 20, each group. But in this, you'd want to have like each square representing a fixed amount of age. So if you see here, we start with 20, end at 65, and so this will be 20, and we'll try to get this to the end being somewhere like 65. So there's 2, 4, 6, 8, 10. So there's 10 squares, and there's we have to cover 45. So that means that each we can do as each small square will be 5. So you can do 30, 40, 50, 60, and then 65. This is the kind of the nicest way I can think of fitting it in. So you can see kind of each of these big squares is 10, and so this one is of course 70. So I'll write 25 as well, 35, 45, and 55. And when it comes to these kinds of questions, you really want so that at least half the area of the graph is covered. So you want make the scale so in that kind of way. So the maximum here is 4.4, So we see 1, 2, 3, 4, 5. So that that lends itself to 1 being each of these squares. So we have 1, 2, 3, 4, 5. So between 20 and 30, it's 2, frequency of 2. So we go between 20 and 30, with a line like this, and then 2. There we go. 30 and 35, it's 4.4. So 30 to 35, it's 4.4, which is, what is that? 4.5. So this must be 4.4. Do my very best to draw a straight line. Of course, please do use a ruler with this. 35 to 40 is 3.2. 35 to 40 is 3.2. Forty to 50, sorry, is 1.3. So we go 40 to 50. 1.1, 2, and 3. And then 50 to 65 is 0.6. So all the way up here to 0.6. And there we go, this is our frequency, our histogram. And I've also got the answer here, in case you don't believe me, which I think looks very much similar. Sorry. Maybe if I send this to back. That's not it. Ooh, okay, it's not letting me. There we are. So I can compare it side by side. Oh, and look, see, I did actually make a mistake here. I ought to have mentioned age in years. So it is important to have units when you do this. So if you spotted that, good job. And then this is obviously drawn a bit neater because they had a ruler, but you can see it's very much the same, and they've got the same scale as well. So that's how you draw something like that. Now we're going to go to another histogram question. So the histogram shows some information about the height of some plants. Work out the estimate for the proportion of plants over 25 centimeters tall. So in this case, you can actually notice that there's no labeling on the left hand column, and that, I guess that would pose an issue if we're trying to find the absolute frequencies. But luckily, we're only trying to find the proportion, and since the scale would be kind of a constant thing, throughout, as at least you'd hope so. If they've done their job properly, it would be constant. So we can figure out the proportion without necessarily knowing the absolute frequency. So what I like to do in this case is kind of figure out, if you think about each little square being 1, and you can say kind of the number of squares in here. So you can see kind of, or maybe even if you wanted to do just instead of doing kind of the area, you can do the height and then times by the area later, the width. So you just find the height of each of these. So this is, if each of these is 1, this is 5, 10, 12. This is 12, 5, what is that, 10, 20, 30, 31, 32. So I'm kind of just, it doesn't matter what you kind of label the frequency density. I can do it 3.2 for all I care, or I could say each of these is 1, and this is 1, this is 2, and this is 2.4 or something. It doesn't matter, because as long as you use the same scale for all of these, when you find the proportion, what you'll do is kind of, you'll look at this, the frequency of the stuff you're interested in, and then divide by total. So if you're scaling by a constant factor throughout, it doesn't matter what you label them as. You just do as what you think it might be convenient. And I thought 5 would be convenient. So 5, 10, 12, 10, 20, 30, 40, 41, 42, 44. This is 12 again, and this is 1, 2, 3. And now kind of worthwhile doing the areas for each of these to find the frequency. So this is the frequency density, right? FD is equal to frequency over width. We've got the frequency density as kind of some value, right? That we've done. But again, as I've said before, it doesn't matter particularly what value we have as long as the ratio is common. We can say 12 is equal to F over W. So if we times both sides by the width, we'll get some sort of measure of the frequency. So we'll times this by 10, so 120. Times this by 5, so 32 by 5. 160. Again, 5 times by 44, 220. 12 times by 10, 120, and then what is that? 20 times by 3, which is 60. So the total frequency is equal to 120, all of those added up together, 120 plus 160 plus 220 plus 120 plus 60. So if we just pop into our calculator, comes out to 680. Now we're looking at proportion of the estimates of the plants over 25 centimeters tall. So we cut this in half. So there's clearly 60 on this and 60 on here. 60 plus 60. So the ones we're interested in is, frequency of above 25 is equal to 120. We'll do 120 over 680. So 120 divided by 680 is 3 by 17. That doesn't sound particularly good of a number, so I'm just going to go ahead and check it again, just in case. 10, 20, 30, 40, 41, 42, 43, 40. That's definitely 44. Definitely 32, 12, 12, 1, 2, 3. That's 5, that's 10, that's, yeah. Okay, yeah, it looks fine to me. I mean, I just check it when I get some dodgy number like that. But I mean, yeah, I've checked it, it looks alright to me. But always good to check your answer. And explain why your answer is only an estimate. Okay, so this requires a bit of thinking. So if you just go ahead, pause the video, and try giving that a go. So the reason it's only an estimate is because when we plotted our data, right, we'll be told that the height for the plants will be given that 20 to kind of height less than 30 is equal to whatever frequency we have here, so some frequency, which comes out to 3/17 of the total. So if we say the total is t, it's 3/17 over t, right? But the thing is, we're not told between 25 and 30. We just assumed it's the half, right? Which isn't necessarily true. We've been given a range here, but we've assumed kind of there's an equal distribution within the range, which isn't necessarily true. So you have to watch out for that. You have to think, I mean, that's the best you can assume, right? You don't have any other reason to assume that it's not going to be equally distributed throughout the range. So you say, oh, assume it's equally distributed throughout the range. I'm concerned with half the range, so it must be half the total. So in that case, it's 60 of our kind of fictitious number. So that's why we assume. So the explanation to answer is that we're using group data, and so we don't necessarily know kind of it's equally distributed or not. So using grouped data, so do not know the exact number between 25 and 30. Sorry for the poor handwriting here. Also, in case you kind of you don't kind of buy the fact that you can use any numbers here for the scale, I really do encourage you to try any numbers you want. Pick the most random numbers you can to think. Say each of these is 3.7 if you want. I mean, it would be a bit harder to calculate the total, but really I encourage you to try it, and you can see why that would work. Because, say if each of these was 1.2, for example, we divide everything by 10, well, we'll divide the total by 10, but we'll also divide this by 10, for example. And by doing that, then, we've done the same thing to top and bottom, and we're left with the same fraction. So again, it's just that thing. It's that kind of, it's that ratio thing, I guess. So, but I do encourage you to go ahead, try this question yourself and make up some numbers that you want on the range, on the scale, I mean. But do be careful. Sometimes, they won't have a proportion, they'll have absolute frequency, and they'll give you a scale. In that case, please don't make up your own numbers for the scale. So hopefully everything in that video made sense, and I'll see you guys